Okay, so here's example 6 that I was trying to do on the board, and I'm going to try to show it a little better. So I'm going to take this cosine functions graph, and I'm going to look at the different areas under the curve of the cosine function using these values. So I'm breaking it up. First off, I'm looking between 0 and pi over 6, and I'm finding this area. Next, I'm going to find the area between pi over 6 and pi over 4. And if we're accumulating, if I add the area that we had here, it'd be this region right here. Next, I'm going to find the area between pi over 4 and pi over 3. So it's that blue area. But if I added the area that we found here, the blue and the black that we had already found, it would be all of this region now. And lastly, we're going to find the area under the curve from pi over 3 to pi over 2. But if we took the area that we had already found there, it'd be all of this added to it. And so this final value, I could look at it as, I actually now know the complete area between 0 and pi over 2, because we added up each of these each time. We added, let me take off my squiggles. We found this area, and we added it to this one, and so we had this complete area now. And then we found this area, and we took all this area and added it over here, and now we have this complete area. And then we found this area, and we added all of this right here, and now we know the full area between 0 and pi over 2. So that's an accumulating idea, how we're adding it up and accumulating the areas. Well, we know from 0 to pi over 2, let me go to the next screen. The interval from 0 to pi over 2 of cosine x dx, I did this on the board with you all, is sine of x evaluated from 0 to pi over 2. That's the sine of pi over 2 minus the sine of 0, which is 1, minus 0, which is 1. Now, if we went back to each of these little pieces, and if we integrated from 0 to pi over 6, and we added to it from pi over 6 to pi over 4, and we added that, pi over 4, pi over 6. Okay, I had to rewrite it and make it all fit, and I just paused it. Okay, so I had to rewrite that to make it all fit, and I had said pi over 6, but that's pi over 3 right there. And then I have skipped the step where I did like sine of x from 0 to pi over 6, and I've went straight to this step for everybody. And now I'm going to skip and just write down the answers I get. Okay, so I've evaluated the sine at all those angles, and I've dropped my parentheses, and we've got several things that are going to cancel. And the only thing left is 1. So we can save ourselves a huge headache if we were to do it this way and trust the accumulating process. So I got interrupted, and someone came in my room, but I think I had finished explaining this, and I think I was telling you about how since we got the same answer, that this was an easier way to go. So that's going to lead us to the second fundamental theorem of calculus, and I'm just going to pause and write that down. Second fundamental theorem of calculus. If f is continuous on an open interval I containing a, then for every x in the interval, the derivative of the integral from a to x equals f of x. So if you look at what really happened, a couple of things. We took the derivative of an interval, and they canceled each other, and we got to plain old f function. And what happened with the variables, we were integrating with respect to t of f of t. So all we really did, it doesn't seem like it should be fair to do, but all we really did was we replaced this f of t with x. So it's equal to f of x. I'll do one with you in a second. So if a function is continuous, this theorem, we can be sure it has an antiderivative. It might not be one that's easy to find or possible to find by hand, but we can be sure it exists. So let's use this theorem. Okay, so we want to evaluate the derivative of the integral from 0 to x of square root of t squared plus 1 dt. We just are going to notice that it's going to fit this perfectly. So all we do is we say it's equal to, all we do is we change the f function to a function with x. So we change it to be x squared plus 1. That's it. Okay, example 8, we're going to find the derivative of capital F equals the integral from pi over 2 to x to the third of cosine of t dt. So we're going to find the derivative with respect to x of the integral from pi over 2 to x to the third of cosine of t dt. Cosine is continuous on this everywhere, so we can use the second fundamental theorem of calculus, and all we're going to do is we're going to say our function at x to the third. Actually, this gets quite a bit more complicated. We have to use the chain rule, and I am not going to cover that type of problem in this video. I'm going to stop this video here for today and post your assignment.